Need to add two more members of our family that we didn't have time to do yesterday. And the first one is what is called the greatest integer function. Okay, I don't remember what number that was. What is it? 7. And the greatest integer function, you will probably remember it better as the stair-step function. And the reason I say that is because that's what it's going to look like after we graph it. It looks like this. F of x equals, and they have this double bracket around x. Like that. Now, it's called the greatest integer function for a reason. Here's the way it is defined. It is defined that every function value equals the greatest integer that is less than or equal to the x value you plug in. And it's really not that hard after you see what it's talking about. It's actually a pretty easy concept. Okay? So let's just try to find a couple function values based on that definition. Let's say that I wanted to find f of 2.7. Now, an integer is a positive or negative whole number. So, what is the biggest integer that is less than or equal to 2.7? 2. Right? In other words, you just go down to the next integer down. What would f of 2.3 be? 2. What would f of 2 be? 2. Because notice we said that is less than or equal to the x value you plug in. Now, as soon as I go down one more, like to f of 1.9, what would that be? 1. Okay? And it works that way if you get into the negative values as well. What if I were to do f of negative 1.6? Now be careful, it's the next integer that is less than or equal to that one. Wouldn't that be negative 2? Right? So if you think of that, when you see the graph, (1, 2, 3), negative 1, negative 2, negative 3. And then 1, 2, 3, 1, 2, 3. All of the values that we plugged in between 2 and 3 wound up with the value of 2. So what you get is, let me use a different color here. What you get is a little constant function right in there, like that. And then we said as soon as we plugged in 1.9, and started going down, we got 1. So all of these in here, all of these will be 1. And if I were to plug in, how about if I were to plug in f of 0.6? What's the next integer down from that one? Isn't that 0? So all of these in here are going to have a value of 0. And it just keeps walking on down like that. That's why we call it the stair-step function. Okay? Its official name is the greatest integer function. But now, what is the domain of this function? Yeah, even though we've got these holes, okay, even though I have a hole there, just at that same value, I have it filled in here. So we are including every x value. The domain is negative infinity to infinity. The range, somebody said all the whole numbers. We need to be more specific than that, all the integers, right? Because whole numbers, by definition, are only positive. So it's all the integers. Okay, those are the only y values where it exists. Okay, so that's the greatest integer function. And, you know, the next function is very critical as well. Maybe more, this is the last one, piecewise functions. And we've seen these, but now we need to be able to start working with them a little bit better. A piecewise function is something like this. F of x equals 2x plus 3 for all of the x's less than or equal to 1, and negative x plus 4 for all the x's greater than 1. Now, when it comes to domain and range and all of those things, for the piecewise functions, it's difficult to make a blanket statement because there's so many ways these can look. I could put a quadratic here and a linear here. I could put any, I could split this thing up any way that I want. So we're not going to make any broad statements, but I do want to go over how would I graph this problem. Okay? If I wanted to graph this, you need to graph it in pieces. Okay? So if you look at my function, I have this kind of changing point at 1. All right, so what we're going to do is let's just get some values, get some hash marks onto my graph. And what we do is we just graph it one piece at a time. So my first piece is 2x plus 3. Now that's just a plain old linear that has a y-intercept of 3, right? So here's 3. There's my y-intercept. Now be careful though. When is the function 2x plus 3? It's when the x's are less than or equal to 1. So here's 1. So 2x plus 3, it is going to be this function over here to the left of 1. So the y-intercept is 3. The slope is 2 over 1, so I could come up 2 over 1, down 2 over 1. Now, since it is less than or equal to, I need to fill in that hole right there. So this function right here is 2x plus 3. That's the first piece of the piecewise function. The next piece, get a different color, getting close to Christmas, I'll use green, is this one, negative x plus 4. All right, so now it is this function when the x's are greater than 1. So you kind of have to do some pretend here because technically it doesn't exist until we get over here. So the y-intercept is 4, so here's 4, and the slope is negative 1. So I need to come down 1 over 1 to get my first point, and I'm going to put an open circle there because it is only greater than, for the x's greater than 1, not greater than or equal to. All right? So my slope is negative 1, so I need to keep getting some more points. Down 1, over 1. Down 1, over 1, down 1, over 1. And there is the other piece of my piecewise function. There is the negative x plus 4 piece. So we have to graph it in 2 halves. All right? In other words, It is this function for all of these values this way, and it is this function for all of these values that way. All right, so you have to split it into two halves and graph them each separately. And the only other thing you have to pay attention to is what I color in. Well, that comes from this. This function said that it was less than or equal to, which is why I colored in that dot. This function just said it was for the x is greater than 1, which is why I left it as an open circle. All right? And we're going to stop there for today.